Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. We will start just by one correction of something that I said last time and it wasn't accurate. So remember we were talking about the margin of a data set, of a model with respect to a data set, and then the margin of the data set, right? And I mentioned that the margin of a model that is not separating the positive and negative regions is not defined. But actually that was not accurate. The margin is defined for any model based on this. So if it's separating, then we compute the minimum distance between the model and the closest point. If it's not separating, then the margin is minus infinity. Okay? Which is very small, yeah, but minus infinity. Okay, it's just a constant. Which means that also there is a margin for any data set. It doesn't have to be separable, linearly separable, because if it's not linearly separable, then all the models have minus infinity margin, so the margin for that data set would be minus infinity. So if the data set is not linearly separable, then the margin of it will be minus infinity by definition. Okay? So this is just a correction of what I mentioned last time. Is that clear? Right. Now back to what we were discussing last time. We were discussing, I think, machine learning application, or machine learning in the context of a bigger application. Did we finish this last time? Do you remember this example? We didn't finish probably. So go through it quickly and then we will move on. So what was the idea here? I wanted to show you how learning is just a step in a much longer pipeline of steps in machine learning in general. So we started with the application of a search engine company that wants to increase their income or revenue, and the idea was to display better ads. So we converted the problem into a learning problem by classifying whether the user will click on a specific on this ad or not. So if I can guess that the user will click actually to that specific ad, which means that the ad is relevant to the query, then I would display it. Okay, that was the idea. So we started then, after defining the learning problem, by collecting the data. So the data, we have a search engine company, so we have users that interact with the system and click and not click, so we can collect the information from that. So that's step 4. Then we need to define what exactly we will collect for this problem. So we said that we need the query, which the user is writing, and the ad that will be displayed or not, and the click. So this is the data that we need for training, right? So we need many examples of this: query, ad, and whether the user clicked or not. So this is what we need to collect. Now we need to represent that data. So last time, I think we, at the end of the lecture, we discussed about how to represent text, right, in bag of words, and we will, inshallah, talk more about that right after this example. So let's, for now, assume that we represented the text somehow. So we have a representation for the text, which is bag of words, for the query and the ad, and also the representation for the click is just +1, -1, based on whether the user clicked on that ad or not. Okay, the details we'll discuss it, inshallah, in maybe 5 minutes. So once we represented the data, what's next is to select the model that we want to train, right? So in the example here, we selected just decision trees, and we said that we will use the depth 20, or we can leave it as a hyperparameter and tune it. Type. All of this, we didn't do any training, right? We don't have even data. We just designed the application. We said how the training data will look like, what's the learning problem, of course, first, and how the training data will look like, how we will collect it, but we didn't do actually any training. So the next step is to select the training data itself. Before we train, we need the data. Okay, so we can select some of the data. Here, the example that we selected, because we are search engine, we have lots of data. We'll select 1 month for training and 1 month for testing. right? Why should we do that? Why don't we have 1 month and we randomly select some of the data to be training and some for testing? Why should they be in different months?
I think because you have to be disjoint.
They have to be disjoint in what sense? يعني disjoint completely. يعني there should not be any intersection between them. Why? Because maybe if there is intersection, there are duplicates, okay, of data. أو يعني very similar examples. If I saw it in training and then I see it in testing, it will be very easy to label it. Okay, so it will not reflect the reality. The reality will be I train on previous data in history, and then in the future I will test the model, right? So the data should be, as you said, should be disjoint. So I will select the training data from April, and later you see that we will predict on May. So we just separate them. Now, once we have the training data, we can train the model. So you see, training the model came at step number 9, okay, from the entire application. So we train the model, and of course we can also train or tune the hyperparameters. If we need the hyperparameters, of course, we have to divide the training data, as we said, to training and div. Once we train, then we can test, right? And then we can evaluate the performance of the model. Okay? So let's say that we will compute the error or accuracy, same thing. If the performance is good enough, then we deploy it. Deploy means we use it in reality. Okay, we put it in the production system of the company. It will be used by real users. Type. It seems like very straightforward, right? The steps are very linear, and it's just a sequence of steps. But in reality, of course, it's not like that. Yeah, for example, what happens if the performance is not good? Repeat what? Number what? We repeat number 9 on the same data. What? Number 9? So we'll go back, and if maybe you mean if we didn't tune the hyperparameters, then maybe we need to tune the hyperparameters, right? Okay, but if we train again, it will probably have the same model, but maybe tuning the hyperparameter will be different. I mean, maybe we didn't tune the hyperparameter in the beginning, and we need to tune the hyperparameter. Fine. What else? Is that the only way we can go? Yes. Changing the learning model, which is changing which step here? 7. So go back to 7 and maybe change the model. Okay. Maybe we need to select another model. Maybe this model is not very good for this task. Yes.
Update the training data.
Update, I mean increase. Okay, increase the training data. Yes, maybe we need to collect more training data. Okay, so we can go back in this case to step number 8 and get more training data. Okay, we can even go back and to step 6 and maybe add features. Okay, change the features. Okay, can we go to step 2 or 1? Yeah, if we failed completely, then خلاص, let's work on another problem. It might happen, by the way. The time is not infinite, right? So if we spend a lot of time, maybe you need to find another way of increasing the revenue. Okay, the point here is that there are 2 points. First, that training a model is just one step in so many steps. So it's a long pipeline. Second, it's not linear like that. You might go in cycles, okay, and retrain the model, reevaluate, and recollect, change the model. So there are many things that can go wrong, or you can improve. Okay, so that's the point of this part. Right. And the rest of the lecture, we will deal with, we will talk about features, how to deal with features. So the first thing what do we mean by features, or how the machine learning algorithm actually treat features? Does the learning algorithm understand what features mean? And if I said that, if you remember the playing tennis example, the cloudy and the temperature and so on, the features, the meaning of the features itself, is it seen by the learning algorithm? No, what is seen by the learning algorithm? The values, the feature values, okay? But of course, for us, we understand the features, okay? So we'll talk about the importance of features later today. But the machine learning algorithm doesn't see the features or doesn't understand the features. It only sees the feature values. So the representation of the features is very important to machine learning models. Usually, we represent features as feature vectors, and we talked about that before, right? So each example is represented as a feature vector. Now, this feature vector has a list of values. There is a value for each feature. So this is a feature value that has a value for each feature, which means it has a dimension for each feature. Okay, so for example, I have this feature vector for one example. So that's one example. You see here, it is numeric in every dimension. So this, for example, this is the feature value of feature number 3. This is feature number 1, this is feature number 2. I mean, dimension 1, dimension 2, dimension 3, and this is the value for feature number 3. Okay, maybe this is, what can be 5? How many years we spent in QU, for example. I hope any less than that. But that can be, right? So, of course, the meaning of the value depends on the meaning of the feature. Right? But they are always ordered in the same order for all examples. Every example is represented by a long vector, and the number of values here are the number of features. There's a value for each feature. Okay? That's probably not new to us, but the distinction between features, values, and vectors is very important. Do you have any question about that? Right. Now, what are the types of features? Not all features are the same, right? Or having the same type. So one type of features is what we call quantitative or numeric features. Okay? Features that have numbers, that have numeric values. Okay? There are two subtypes for numeric features. Binary, that has only 2 values, like what? Huh? Yes, these are the values, but I mean, what is the feature? Give me an example of a feature that is binary, naturally.
Yes and no.
I understand, yes or no, these are again the values. What is the feature?
The person has COVID or not.
COVID or not, يعني ما لقيتيش غير طيب, yes, يعني infected or not. Okay, that's a binary feature. Gender is binary, yes. Okay, so there are many features that are binary naturally, right? So usually we represent them, in general, we or most of the models will need all the feature values to be numeric. Okay, so in this case, even if the feature is true or false, we'll have to convert it into numbers. So usually we use 0 or 1 or -1 and 1, okay, to represent the values. Of course, the easiest one is the real valued feature. Okay, so we'll just use the value, like the GPA, like temperature, like salary. These are naturally real valued features, so we'll just use the value that we have. Okay, so this is numeric features. Type. Do we have other types of features? Because we have quantitative, we have to have qualitative? No. Okay, what? How do we? Can you give me example of? And of course, we have this. This is numeric, right? So we have to think about non-numeric features. Color. Very good. Okay, so color has what could be the possible values of color? Yellow, green, blue, white, red, right? Okay, so this type of features, we call it categorical features. We don't call it qualitative features. Sorry, yani, it's misleading. Quantitative and not qualitative. Non-numeric. Okay, quantitative here means numeric, and we are talking about non-numeric. So categorical, like, as you said, color, red, green, blue, yellow, and so on, or the genre of an article like sports, health, educational, and so on. Okay, so these are the feature values, right? Okay, type. So this is yes. We'll get to that. We'll get to that. I said, يعني maybe a couple of minutes ago that we need to represent all features as numbers eventually. Okay, but we're talking about the types now. Then we will care about how to represent them. Type. This is the categorical feature. Now, is there any order between these? And can I say, مثلا, blue is greater than red? No, there is no order, right? But there are also features that are categorical, but they have ordered values. Like what? Like low, medium, high. These are categories, right? But they also have order between them, right? We know that low is less than medium, less than high, right? Or large, or whatever. Okay, there is order. These are called, sorry?
No, I mean weak or strong.
We what? Weak or strong, yes. Weak, very weak, strong, very strong. Okay, so there is order between the feature values. Yes, actually I have this. So this is called ordinal features. They are subtype from the categorical, still they are categorical, but the categories, which are the feature values, are ordered. Okay, so low, medium, high or large, weak, fair, strong, very strong, positive, neutral, negative, right? So there is order between them. So the difference between categorical and ordinal is clear. Type. Now let's care about what you mentioned about mapping these in a feature vector. We said that feature vector has to have values, right? Numeric values. Type. Quantitative is straightforward, right? It's already numerical. So what should we do with the others? Let's start with ordinal, because it's a bit easier than categorical. Ordinal. What should we do with ordinal? How can we convert this into numbers? Yes, so we select values, okay, that represent the order. Okay, so as you said, -1, 0, 1. And for example, maybe negative would be -1, neutral would be 0, positive would be 1. Okay, we can also do 0, 1, 2. But some numbers that are, of course, reflecting the order of the values. Okay, so this is also looks like straightforward, right? So if I have high, I will put 2. If I have medium, I will put 1. Low, maybe 0. We can -1, 0. 1. Sometimes we even do it that way, 1, 2, 4. If we think that the last one is really much larger than the second one, it depends on the meaning of the values. But it's straightforward, right? So we just put numbers here. Type. How about categorical? Can we do the same with categorical? And for example, can we assign 1 to red, 2 to green, 3 to blue, and 4 to yellow? Can we do that? We can, of course, right? Theoretically we can, but is that good or bad? Or in other words, why is that bad?
I mean, like, for example, if red was 1 and blue was 4, you're giving blue more value than red.
Exactly. It's like we are ordering them, but they are actually not ordered. If we give green 2 and red 1, the algorithm will assume that this is double the value of the other one, right? So it might affect, of course, the model, the learning itself. Type. Here's the solution. In this case, in this case, how many feature values we have here? 4. So I will convert this feature to 4 features. So one feature will be called red, another green, third blue, and fourth is yellow. Okay, so instead of having just one feature, I will have 4 features. But where are the values? Let's say that one example, specific example, was green. So I will put only 1 in the green feature, and the others will be zeros. So if the example actually has a green color, it will have 0, 1, 0, 0. Okay? Type. How about if it's blue? 0, 0, 1, 0. And so on. So every example will have four features, two feature values, and only one of them is 1 and the rest are zeros. This is called one-hot encoding. One-hot because there is only one. All of them are zeros except one, which represent the actual value of the feature. Okay, so this is called one-hot encoding. But now every column here is a feature. So we converted one feature, one categorical feature, into how many features? 4 for this example. For this example, for this one, how many features we will have? 1, 2, 3, 4, 5. Okay, 5. So if we have n categories, then this categorical feature will be converted into n binary features. Actually, if you look at every feature now here, it is binary, right? It's either 0 or 1, right? So we convert the categorical feature that has n feature values into n binary features, right? And then we deal with the binary features as usual. Okay, is that clear? Any question on this? So now you understand how we deal with the different types. Yes.
So this would be converted to its equivalent.
Can you raise your voice, please?
It would be converted to its equivalent. For
To
example,
coordinates.
equivalent number.
Yes. Let's say that the example has color feature, right? Here the example has red. So I will replace red by 0, 1, 0, 0. This is green. Green. I will replace green by 0, 1, 0, 0.
But
Okay.
I mean it would be 4, for example.
It will be
4.
yes, 4 values, 4 features.
No, 4 decimal.
4 what?
And decimal.
In decimal. No. It will be 4 binary values. 0, 1, 0, 0. Because each one of these now will be dealt with as a feature, as a different feature. It's like a separate binary feature. Because it's like red, true or false, right? Every feature of these is like true or false. So when we have originally green, then red is false, green is true, blue is false, yellow is false, right? So it's 0, 1, 0, 0. Yes? Here it doesn't matter. It's a vector anyway, and you can deal with it as column or
Another way of doing that, giving them like a binary number, 0, 0, 1, 0, 1, and then 1, 1.
Okay. I will leave that to you. Think about it, whether this will be a good solution or not. Okay. So what she is suggesting is that instead of doing it that way, we can do it as binary digits, okay, or binary numbers. So instead of having 4, we can say 0, 0, or 0, 1, or 1, 0, or 1, 1. So we assign each of the 4 values, green, red, blue, and yellow, to one of these. Okay? Did you understand what she's suggesting? So instead of having green to be 0, 1, 0, 0, maybe green would be 1, 0 only. One of them. Okay? It will be different from the others. So I will leave it to you to think whether this is a good solution or not. Okay? I will leave it to you to think about whether it is good or not. Right. Now, now let's think about text features in particular that we started to talk about last time, right? So the problem with text is that we cannot deal with it directly in machine learning, right? Why? Why is that? Because they are not numeric, right? Because they are not numeric. So we have to convert it into numbers. What type among the types that we saw in the previous slide is text? You said that. Why is that? What are the categories?
The number, the letters.
The words, okay, the words. So we see the text is composed of sequence of words, so we can think of, because the words indicate the meaning, so we can think of words as features here. Okay, so every word is a feature. Every word can be a feature. It's like, yes, it's like categorical, but we have so many values, so we convert it into many features. Each word will be a feature, and this is what we called last time bag of words. Okay, so we ignore completely the order, and we just keep the words themselves without the order. That's why we call it bag or a set. You know, in mathematics, a set doesn't have any indication of order, right? It has just some items, okay, without the order of them. Type. In this case, we will deal with each word as a feature, right? As a binary feature, right? We can think of it that way. So the value of the feature will be 0 or 1, based on what? Based on whether the word appeared in the document or the text or not, right? And that's what we discussed last time, right? So we said that the feature vector will have zeros or ones based on the words that appear in the text. So let me show you an example. This is an example that has, it's nice if you read it, but it's just 5 short documents. Each of these we want to represent as a feature vector. Okay? Type. Now, we said that we will use the words as features, right? Okay? So, how many features we have? This is the number of words, right? Number of unique words. If you count the unique words here, I think there are 11 or 12. So, if we want to represent just these 5 documents, we'll have to have a feature vector for each of these documents, and the length of that vector will be, let's say 12, because we have 12 different documents here, different words here. Okay? So the representation will be something like that. Here, the feature vector is a column. Okay? So each column here is a feature vector. So this is the feature vector for document number 1. You will see that it will have ones only for the features that, for the words that appear in that document. So we have one here because he appeared in D1. And we have one here because likes appeared in D1. If a word didn't appear in D1, like and, we will have 0 in that position. Okay? So this is one feature vector for the document D1.
Doctor, and the
Yes.
number of the values will be the same as the sentence, but not repeated, right?
Yes, we will assume here that the feature values are binary. So it's either 0 or 1. If the word appeared whether once or many times in the document, the value will be 1. Okay? If it didn't appear at all, the value will be 0. Okay? So you will see that the word he, for example, appeared in all documents. That's why it's 1 over all over. Likes is the same, 2 the same, but wink, for example, it didn't appear in D2 and D3 and D4. It appeared in 1 and 5 only, and so on. Yes.
دكتور هو في الكلمات نفسها بنعمل نفس الموضوع لأن في الكلمة هي مثلا لازم نعملها convert
ما هو this is ما هو okay احنا we converted the text, every text or document here we converted it into a feature vector type. What are the features? Every word is a feature. Every word is a feature. Now the next question is what should be the value of the feature? So the word, for example here, ink, okay, it didn't appear in D1. Still it's a feature in D1, by the way, but the value of it is 0 because it didn't appear in D1. It appeared in D3, so the value of it is 1. Okay, so every example here, so every document here is an example. How many features we have? The number of words. We call it, by the way, vocabulary, which is the different words we have. Okay, we call this list of the vocabulary. So the size of the vocabulary, which is the number of words, is the number of dimensions that we have. Okay, this is of course a small example, but if we are talking about English, we'll have thousands of words. Okay, so thousands of features in this case. Okay, but most of the values in any feature vector in this case will be zeros because a document might have few words, right? We do not have so many words from the dictionary, right? And it might have 100 or 200 out of tens or hundreds of thousands. Okay, so most of the values in any feature vector, in this case in text, will be zeros. Okay, any question about this? Type. This is when the feature values are binary values, but we can think of maybe different representation or different, not representation, but different feature values. As you said, someone said here, we can count how many times the word appeared. Instead of just saying 1 if it appeared, we can put the number of times it appeared. We call it frequency. Okay, so for example, the word he appeared actually twice in D1. So we can, that's a different representation now. We can use the frequency values as feature values, or the counts as feature values. So we can put 2 here, 2 here, 2 here, 3 here, because the word drink appeared 3 times in D2, and so on. Okay? Is that clear? There are other ways also to find the feature values, but we will not discuss now. But binary values are used, counts or frequencies are also used. Any question about this? Okay, so that's the end of talking about text features in particular. Now let's go back and talk about features in general. And we will start by talking about the importance of good features. Now imagine that the data that we have, all of the features are very bad. What do you mean by very bad?
Not usable.
Not usable. What do you mean by not usable? They are not good for the task that we are trying to achieve. Okay? And you remember the example of the color of the eyes of the person? Doesn't matter, and if the color of the eye is brown, to decide whether the person should get funding or not, for example, from a bank or something like that, a loan. So this is like a bad feature or irrelevant feature that will not help us in our task. And now imagine that all the features are like that. Will we be able to get a good classifier or a good model in general? Of course not, right? So that's what we mean by garbage in, garbage out. If the features are garbage, if the features are bad, then of course we cannot expect the model to just train magically to be a good model. Okay, so if the input is bad, then the output, of course, will be bad. Time. Now, I can use the existing features and try to do some combination, and we saw that last time. Remember feature combination when we started by a feature x and then we added x squared. When we did that, the data set became to be separable, right? Linearly separable. That was good. So something like that sometimes will be good, is to take the existing features and try to make combinations of them, or to add good features, which is called feature engineering. Okay, so we try to find good features for the task. This sometimes will give us a boost, a large boost in performance, maybe larger sometimes or most of the times than tuning the hyperparameters of the model. Tuning the hyperparameters might give us improvement in the performance, but in most cases, designing the features and finding good features and maybe combining some of the features will give us much higher. Okay, so this is just indicating the importance of what we call feature engineering, is to find the good features for your task. Right. We talked about irrelevant features, right, or the bad features. Another example of a relevant feature is the word the. Now we said that in text, every word will be a feature, right? So the word the, it appears in almost every document we can see, right? In almost every document. So you can think of it as useless, right? It doesn't tell us anything about maybe the topic of the document, or whether this review is positive or negative. Okay, so usually the word that, because it appeared in everywhere, it's useless. So this is another example of irrelevant feature. There is also another type of bad features, which are called redundant features. What do we mean by redundant features? A feature might be good, might be important for the task, but we have multiple copies of it in the data. Okay, so there are maybe two features that are exact copies or very near duplicates, yani very similar to each other. So one of them might be useful, and the other, of course, is not. But that might affect badly the model if the model doesn't. If there's no way by the model to find out or to remove or filter out the copy feature, it might be affected badly. Okay, so an example of a redundant feature is the pixels that are close to each other in an image. Pixels that are close to each other, probably they will have the same color, right? So it's like a redundant to consider them as different features. Right, let's think together about the effect of this in decision trees. Let's say that, remember the example of playing tennis? Let's say that we take one of these columns, which are the features, and repeat it. Yani, there was, I think, a cloudy feature, I think. Let's say that we have cloudy 1 and cloudy 2. And they are exactly the same. Same means it's for every example, the value is the same. Okay? Now imagine what will happen when we train a decision tree. How it, will the decision tree will it be worse if we have something like that or not? Let's start from the beginning. In the beginning we select the feature for the root, right? We have all features, right? We select one from all of them. How do we select? We score each one, right? Remember there is a scoring mechanism. 50 years ago we discussed decision trees, right? There was a scoring mechanism, right? Accuracy or entropy or Gini or whatever. We give a score for each feature and we select the best of them. Right. What will happen in this case when we have two features that are copy of each other? What one? No, not the accuracy. I'm talking about the scoring. What will happen in the scoring? You will have the same score, right? These two features will have the same exact score because they are exactly the same. They are exactly the same. So they will have the same score, right? So let's assume that this is the highest score. So we will choose one of them maybe randomly. Let's say we choose cloudy 2. Okay? What will happen after we choose cloudy 2? We look at the branches, right? But before that we subset the data, right? We get a smaller data after we selected that feature, right? Do you remember? Okay, we discussed that when after we select the feature, we get a smaller subset of the data, right? After we get the smaller subset of the data, we rescore the remaining features. Right. Now we selected cloudy 2, right, already. So cloudy 1 is only available, plus the other features. Do you think cloudy 1 now, after we get the subset, the new subset, will be important to be selected? I mean, will have a high score? In most cases, no. Okay, in most cases, no. Because we already selected it. It was beneficial already before, and we now focus on the data that in which the other features will be important. Okay, so this feature, most probably, with very high probability, it will not have a high score. Okay, it's like it's already used. Okay, it was good in distinguishing in the previous stage, but in that stage, most probably it will not. Okay, so in this case, it will not be selected, and decision trees will not be affected, in of course most cases, by the redundant features. Okay, is that clear? Yes. Yes, of course, it will affect the time, but in terms of performance of the model, most probably it will not be affected. Okay, is that the case with KNN and perceptron? I will leave that to you. Okay, so think about it. Think whether the irrelevant features will affect KNN and perceptron or not, and the redundant features also. When we have a redundant feature, will KNN be affected or not, and perceptron will be affected or not? Okay, and we'll have to stop here, inshallah, talk to you see you on Thursday. Assalamu alaikum wa rahmatullahi wa barakatuh.